examples of curves. And for this, let's start with our favorite example, the easiest one, which is P1. So P1, this is a curve, and it is a smooth curve. Okay, so it's just a line. Now I can consider a second curve. I'm going to call it Q, which is y squared equal xz. And here now I'm going to assume that the characteristic of my base field is not 2. And I say that these two curves, actually, they are isomorphic. So they would be, in our sense of trying to understand this object, the same object. And so let's see this. So how can I define a map from P1 to Q? I guess, this is quite something that you may have encountered before, because it's just like parametrization of conics. So here, if I take a UV, I'm going to send it to, so let's see, probably y is going to be UV, U squared, and V squared. Does that work? So is it really like first a point on the curve? So UV squared, that's U squared times V squared, is U squared times V squared. So yeah, so at least I'll call it phi. No, I didn't give it a name, so let's call it phi. So at least, it maps a point here. But now, of course, you need to check if it is a morphism. So what happens? You don't want this to be 0, 0, 0. So when can this be 0, 0, 0? For instance, if you have, what do I want to say? You should have, for instance, if you have u equal, if you have u and v different from 0, this is never going to be 0, right? The only possibility for these three numbers to be 0 is u and v to be 0, but this is not a point of P1, so this map is always defined. So you really have a morphism. Now, we have to try to define a map in the other direction. So let's say now we have a map from Q to P1, and I'm going to associate to x, y, and z. This time I'm going to look at it, x and y. Right? Yes, x and y. So let's call it C. Obviously, this map, is defined. At least generally. It really take a point of Q to a point of P1. I can always do this. But now, we have to see if it is really defined everywhere. Is it a morphism? So it's not going to be a morphism if only if x and y are both 0. Is 0, x and y 0, 0 a point of the curve? And yes, it is one. You could have x equals 0, y equals 0, and then it means that z is equal to 1. So it is defined everywhere, except maybe at the point, so C might not be defined at the point 0, 0, 1. But now we can play with the equation. Maybe this is not the only way I can write this map. And yes, that's what we are going to do. But look that xy inside the ring where, y squared equal xz, I can write it, x, I can replace it by y squared over z. And now I can eliminate y on both sides to get y over z and 1. And now I can replace z by 1, y by 0 to get the point 0, 1. So what I have proved is that, nope, C is defined at 0, 0, 1, and the image of this point is the point 0, 1. Okay. And the first thing that we have to to realize, I mean, it can sound like, wow, we were really lucky. I mean, we had like a map, rational map, and it turned out to be a morphism, is that this always is the case. I mean, this is a very nice property of smooth curve. So proposition, which is proposition proposition 3.2.1 in the notes, is that if you have phi, a rational map from a smooth curve to a V, which can be a variety, it's not necessarily a curve, inside a Pn, then phi is actually a morphism. So this is quite nice. Okay, the other thing, so now I'm coming back to my example. What you can do is, of course, you can take the map phi, so that's u squared uv v squared, and then you push it back to u squared uv. So if you do the composition of phi and psi, what you get is you have sent uv to, let me see, uv to u squared uv, which is uv. So psi phi is the identity on the function field. And because there are two morphisms, this is really an isomorphism. So what we have proved that P1 is actually isomorphic to Q over the field K. So sometimes when I want to make precise over which fields it takes place, I will put small k next to the isomorphism. So they are the same object. I mean, they seem to be different, but they are the same object. So what we say is that we have two different models of the same curve, and they are smooth models. I mean, now, I mean, we could also degenerate it a bit. So there is a quiz. What can you say about y squared z equal, so I took x cubed. Huh? So is it smooth? First question. Or actually, is it smooth? And then can E be isomorphic to P1? So, well, I mean, if you do the math, you will see that it is not smooth at the point at infinity. So not smooth, not smooth at 0, 0. And because an isomorphism, I mean, locally, it's going to conserve all the properties that we have of a local ring. In particular, if you have a discrete valuation ring, it should be sent to a discrete valuation ring. So you can't have two curves isomorphic with one singular and the other one which is not singular. So not smooth at 0, 0, which implies that E cannot be isomorphic to P1. But the story doesn't end here. Let me tell you a bit more. So we are still going to define some map. So first I have a map E to P1. So which at x, y, z maps to x and y. As I said, you can always, y and x. I have changed the order. And then I'm going to take a map from P1 to E, which at u and v maps to u squared v, u cube v cube. Okay. I mean, first, as always, we have to see that they are well defined. This one, there is no problem. And this one, so if you do y squared, so u6 times v cubed, this is the same as u squared 3, so u6 times v cubed. So, I mean, at least it is well defined as a rational map. And because of this proposition, that we know that this map from P1 to E is necessarily a morphism. So we have a morphism that I call psi again, let's say. So this is a morphism. Now what about phi? I mean, first, let's do the composition phi psi. So if I do this, I start from x, y, z. So I get y and x, and I map it again here. So I get y squared x, right? Y cubed and x cubed. Well, it doesn't look like anything special, but now you can use the fact that sorry, maybe I wanted to use the point z instead. Huh? That would makes more sense. Let's see. No, maybe not. No, it's okay. That's right. So that's y squared x, y cubed, and now I can replace x cubed by y squared z. Cancel y squared, and I get x, y, z. Perfect. So it means that these two maps seems to be inverse of each other, at least as rational maps. And of course, I mean, if moreover there would be morphisms, then I would have an isomorphism. And I said that they are not isomorphic. So this map phi is not a morphism. Okay, it is not, for instance, defined well at the point 0, 0. All right, but still it's interesting that you have two maps which are not morphisms, but which are inverse of each other inside the function field. And it is as interesting as it has a name. So what we say that, so E and P1 are birationally equivalent. Meaning that, so you have now a map from, so in general, if I take a curve C1 and C2, saying that they are birationally equivalent means that you have an isomorphism between k bar of C1 and k bar of C2, which is simply given by, if I take the map C1 to C2, which I call phi, and a function, so is it in the right direction? Probably not, we'll see. I want to define, if I have a function on C1, I want to define a function on C2. So I have to do it in the other direction. So I start with C2 and C1. So if I have a function on C2, so it is going to be a map like this. Well, let's do it to the rational, let's say, yeah, to k bar. Then I can make it a map of C1 simply by composing with phi. So this is what I denote phi star of f, which is just f on phi. And this map, I mean, it has an inverse if they are birationally equivalent, and this map is then an isomorphism between my function fields. Okay? So to repeat it in another way, so two curves are going to be birationally equivalent if and only if they have the same function field. Okay. So we have now two different notions of equivalence. We have isomorphism, which is the strongest one, and we have this weaker notion of being equivalent. So let's try to make a picture. So this is going to be all the curves which share the same function field. So inside, I'm going to group them by isomorphisms, okay? Because, I mean, isomorphic objects over the field, I mean, they really share the same properties. So I can really put them in the same package and not try to distinguish them. So like this, I have packages. So of isomorphic objects, so isomorphic curves. What I know is that, well, here, as I started with the curve C, which was smooth, so here is my curve C, smooth. And all the other objects that are isomorphic to C are smooth as well. So this is the smooth package. And there is only one smooth package, because we have seen that if you would have like a curve here that would be birationally equivalent to the curve here, but at the same time these two curves would be smooth, then the proposition which is still on the blackboard over there shows you that, I mean, these two curves would actually, I mean, the two morphisms would be, the two rational maps would be morphisms, and so the two curves would be isomorphic. So these two blocks, these two packages would be the same package. So there is only one smooth package. So that's the only unique smooth class. Okay, all the other ones are singular objects. And now there is one other nice package. I mean, it can be the same as this one. I don't say that they are necessarily distinct, but at least there is always one which contains a plane model, but which can be singular. And this is the consequence of lemma 3.1.1, that there is always a plane, possibly singular, model. Okay? And that's quite cool because it means that it is only defined by one equation. It means that this what you have is actually that k bar of C is always a k bar of x and y divided by an equation so it's a fraction field of this, where f is your defining equation. Is a plane model. So it is quite cool because it means somehow that once you have a plane model, you understand this big thing. And if you understand this, it means that somewhere there might be a curve which is smooth. But maybe not. I mean, now if I start with a singular plane model, I can define the function field, but maybe it's not clear that there is always a smooth model inside. And even more generally, with k bar of C, I could consider, I know that k bar of C is necessarily a function field of transcendence degree 1, and I could consider all these fields, like very abstractly, and I could say, does it correspond to a curve? And in particular, does it correspond to a smooth curve? And that's the very nice result now, is that it does. I mean, this way of looking at object really enables you to pass from function field theory to curve theory. So this is going to be the theorem 3.2.3, which says that so any field of transcendence degree with a bit of restriction, which is that the intersection with k bar is k. So this is just to preserve the arithmetic as well, is the function field of a smooth projective and absolutely reducible curve. Which is, because we have seen it here, unique up to k isomorphisms. And that's why it's so nice. I mean, that's why smooth is so nice, because once you give yourself the function field, it defines a unique object in this class. So it is really somehow the best object that you can hope for. And moreover, this, so here you have somehow an equivalence between smooth curves and function fields. And now you can extend this correspondence between the objects to morphisms. So this correspondence extends to morphisms, where morphisms between curves become injections of function field. And I should say non-constant morphisms become injections of function fields. Just a word to be a bit cautious here. When one has always to distinguish very carefully the notion of isomorphisms over the field and over the algebraic closure. Okay, I mean, for instance, if I give you the curve y squared equal x cubed plus 1, and the curve y squared z equal x cubed plus, what do I have to put here? Plus 27, I guess that's going to work. Still on the other page. Yes, except just to be careful, I have to be projective everywhere. So these two curves, so quiz, they are isomorphic over q square root of 3, but not over q. You can try to prove this, and this part is easy, this part might be a bit harder, but seeing that maybe you can reduce them over a finite field and try to see, what it says about the number of points. Okay. And so these objects that are related, that are isomorphic over an extension but are not isomorphic over the ground field, they are called twists, and this is also a very interesting part of the theory that we might see a bit later. All right, I have almost done with this part. One last thing I want to say is that you can take really advantage of this equivalence between function fields and curves to extract plenty of properties you know from from field theory, to use them inside the world of curve. And for instance, definition of what is the degree of a morphism. If you have a morphism phi, non-constant, between two curves, then what you can do is that you can take the function field generated by C2, and we know that it gives an injection by phi star inside the function field of C1. And I can define the degree of phi as the index of phi star of this field inside this field, just as an extension of field. It's a finite extension, and I can define the degree of my map in this way. And this could give us, like, I mean, we are still looking somehow at a proper definition of how to classify our curves. And for plane curves, we used the degree. But I mean, that worked only for plane curves. Here we could say that maybe another nice thing is that we could take, so first, I mean, you have to realize that when you have a function between on a curve, it can also be looked at a map to P1. That's the first thing. So looking at map to P1 and speaking about functions, that's the same. So I have a phi like this, and I could look at the curves with, which have a phi of minimal degree. I fix, for instance, phi of degree 1. So which are all the curves which have a degree 1 map to P1, which are smooth. I mean, then, I mean, because it's a degree 1 map, it means that the two function fields are the same. And as the two curves are smooth, it means that the two curves are isomorphic. So there is only one curve with a degree 1 map to P1, and it is P1 itself, up to isomorphism, of course. Okay, so that's a bit boring. And then I could say, okay, let's look at degree 2 map, and maybe at degree 3, and so on, and that would give us a nice classification. So in the manuscript, the exercise 3.5, look already at the very interesting example of degree 2 maps to P1. And using, indeed, like some elements that you know from field theory, you can find the shape of all these curves over, let's say, a field of characteristic different from 2. So that's nice, but then, I mean, what you realize, I mean that's the solution somehow of the exercise, is that you can write them y squared equal f of x. I mean, that's going to be a plain singular model, but still, with, so f, a polynomial in x. And you see that it's not so good as a replacement for the degree, because now, I mean, if f is a finite field, well, if k, sorry, is a finite field, f can have still any degree as you want. So there is not a finite number of such curves which have a degree 2 map to P1. And one nice property that we really want to preserve in this classification of curves is that we want, when we fix the finite field, and we fix this invariant that the curves, there is only a finite number of them up to isomorphisms. So, I mean, this is not going to be the right definition, but it's still a nice way to classify curves which have like nice models, because of the degree to P1 is going to be small. Okay, so one last notion I want to tell you today is differentials. So this is a part of the note which is section 3.4.1. So if you don't know about differential, you should read it before looking at the rest of this lecture. So what you find in particular is that there is a space of differential, and it is a vector space over the function fields of the curve. So it is a vector space of dimension 1. So what it means is that if I take 2 omega 1 and omega 2 here, then I can write omega 2 as f omega 1 with f inside k bar of c, right? Now, in the same way as for functions, there is a notion of divisor. So the divisor, you can define the divisor of a differential. And the divisor of omega 2 in that case is going to be the divisor of f plus the divisor of omega 1. Good. And now what? The thing is, we can look at degrees. So this is going to be the degree of the divisor of f, but what we have seen is that the degree of a divisor is always 0, plus the degree of the divisor of omega 1. And what we see is that the degree of a divisor of a differential doesn't depend on the differential. So this degree, it is an invariant of C. And it is going to be the good invariant we are looking for, or almost. What we will see in the next lecture is that this degree is actually equal to 2g minus 2, where g is going to be a non-negative integer, which is going to be the genus of the curve. So, I mean, it's another way to see where the genus is by the degree of this divisor. So, the only thing I want to do now with you to finish for today is look at one example when we try to do all these computations that with the notions we have introduced today. So I'm not going to do anything in a smart way, okay? I'm really going to just take the definition and try to apply them and do all the computations. So 2 examples. I mean, the first one is inside the note, so it's the example 3.8, where you have the case of P1, and where you prove so that the degree of the divisor of a non-zero omega, so I should maybe say here that I want omega 1 and omega 2 to be different from 0. So the degree of the divisor is going to be minus 2. So if I look at the formula over there, it means that a P1 should indeed be a curve of genus 0. And the case I'm going to do with you is the case, the following one. So y squared z equal x cubed minus x z squared. Okay? So first thing that you should prove is that C is smooth. Okay? So this I'm not going to do it. I mean, you just apply the criteria as always. The second thing is that once it's smooth, we can try to find uniformizers at all points. So I'm going to distinguish the point at infinity. There is only one point when z equals 0. So when z equals 0, you must have so y square, so z equals 0, so it means x cubed equals 0, and so x equals 0 and y equals 1. So there is only one point at infinity that I denote like this, which is the point 0, 1, 0. Here I should say maybe also that characteristic of k is going to be different from 2. So this is the point 0, 1, 0. And okay, so let's look at this point. At this point, I can rewrite my equation locally as y squared equal, as z equal x cubed minus x z squared, right? I let this term goes over there, so I have z times 1 plus xz equal x cubed. And now I'm happy because 1 plus xz, when x and z are 0, I mean at the point 0, 1, 0, I mean this is 1, so this is invertible in the local ring. And it means then that between the two generators of my maximal ideal at 0, 1, 0, I mean z and x cubed, z can be expressed as x cubed. So the uniformizer at infinity, so t of infinity is going to be x. And z is going to be the order at infinity of z is going to be 3. Now I have to look at all the other points, all the affine ones. So let's take an affine point. So AB1, an affine point. Okay, it means that what I have, b squared is equal to a cubed minus a. That's the equation I have. And now I have, well, at a and b, of course, I mean, what is going to be two functions that are going to be 0 at that point? I mean, there is going to be x minus a and y minus b. So I should express a relation between x minus a and y minus b. So let's start. For this, you take x minus a cubed minus x minus a. So I'm mimicking the equation x cubed minus x, except that I translate it a bit. Then, I mean, you do the computations, and after a while, so you find that this is y squared minus b squared minus 3a x minus y a squared minus 3a squared x minus a. Okay, so that you can rewrite as x minus a cubed plus 3a x minus a squared plus x minus a 3a squared minus 1 equal y minus b times y plus b. And now we shall distinguish two cases. First, b is different from 0. So if b is different from 0, then y plus b is not going to be 0 at when y is b. So if b is different from 0, b plus b is different from 0 because I'm not in characteristic 2. So this element is invertible, which means that I can express y minus b in terms of x minus a. So as a conclusion, I get that x minus a is the uniformizer. Now, the case where b is equal to 0. So when b is equal to 0, I mean, this is y squared. Now, let me look at this equation. So I can rewrite it x minus a times x minus a squared plus 3a x minus a plus 3a squared minus 1 is y squared. And again, I would be fine. I would like to express now x minus a in terms of y. Okay? It is possible if this term is going to be invertible, and it's going to be invertible if this is not 0. But now what does it mean from we are at the point where b is equal to 0? So what are the values of a? If b is 0, then you have a cubed minus a equals 0, which means a times a minus 1 times a plus 1. So a must be 0, 1, or minus 1. So if I plug 0, it gives 1, minus 1. If I can plug 1, it gives 2, which is different from 0 in characteristic 2. And minus 1 gives also 2. So this is never 0. So it means that this time, so y is the uniformizer at all the point 0, a0. Okay. So we have found now all the uniformizers. So now I'm going to take a differential. So I'm going to take the simplest one, dx. So we have several possibilities. First, I mean, let's look at an affine point AB. Because of the rules on differential, d of x is the same as d of x minus a. And now I'm done when x minus a is a uniformizer, because the rules to compute the order of a differential at a point is to express it as a function times the derivative of a uniformizer. And x minus 1 is a uniformizer when b is not 0. So from this, I have that the order at ab of omega is 0, because the function is constant, when b is different from 0. Now when b is 0, it's not x which is the uniformizer anymore, it's y. So I have to change my dx in a dy. So what is the best way to do this? The best way is to look at the equation. I have y squared equal x cubed minus x, right? That's my equation, I think. Yes. I mean, affinely, this is the one. Now, I take the derivative a bit like a physicist on each side. So I have 2y dy, which is 3x squared dx minus dx. So what I see is that dx times 3x squared minus 1 equal 2y dy. So dx is 2y dy over 3x squared minus 1. And now I'm done, because the order at a point a0 of omega is going to be the order at a point a0 of 2y over 3x squared minus 1. Y is the uniformizer, so its order at the point a0 is 1, so this is 1. Okay? So I have done all the affine points. What is left is the point at infinity. So for the point at infinity, we have to be a bit cautious, because I have not been so cautious here. If you look, I mean, I have directly written things in an affine way. I have said, let's omega equal d of x. But x is not a function on my projective curves. It should be x over z that I meant, meaning that I look affinely, so I put z equal to 1. So what I really want to look now is x over z. But now, so what is going to be, I mean, at infinity? How are we going to look at these things at infinity? So we are going to look at d of x over z. And what is the uniformizer? So remember, at infinity, the uniformizer was y, but again, it was not, it was x. It was x, but actually it was x over y as a function when y is equal to 1. That's really maybe a subtle point. I mean, so often, I mean, we do an abuse of notation, like looking at a function as on a local affine chart, so they become really like more polynomials, but you should really think it in that way. So the uniformizer is x over y. So I shall express x over z as something depending on x over y. So I'm going to write it like this. And now, well, you do the classical formula for derivative. You have a z over y squared here. So you derivate x over y, and here you have a z over y minus, so x over y times d of z over y. All right, and now I'm almost done. So I have, first, I can replace all the y now by 1. Now I'm again looking just locally. This is just to simplify a bit the thing. That's going to be my dx minus x dz over z squared. So what I know is that z, so what I have, I know the expression of z. I have it here again. Yeah, so z was x cubed over 1 plus xz. And I can use the equation of the curve also again to find that d of z, as I did before, is 3x squared minus 2xz over 1 plus x squared dx. Okay, I put all these things inside. And I found that this expression is going to be 1 over x cubed minus 3 over x cubed dx plus 1 over x squared something dx plus and so on. The idea is really to separate things now by the orders of the highest degree of the poles. And so here what I find is that as I'm not in characteristic 2, there is always a pole of order 3. So the order of dx at infinity, after all, is the order of this function, which is minus 3. So what I have proved, so conclusion, is that the degree of the divisor of dx is 1. So is it still here? So yes, 1 for each of the point a0. So how many are there? There is 0, 0, 1, 0, minus 1, 0. So it's 1 plus 1 plus 1. So there are 3 zeros. And then at infinity, there is a pole for my differential of order 3. So I found 0. And if I believe that this number should be of the form 2g minus 2, it means that I'm dealing now with a genus 1 curve. Okay? And just a nice remark, of all this computation is that what you see is that the curve we started with, the curve C, as it has a degree of a divisor which is not minus 2. This gives you just a reason to believe that, your curve is not a P1. It can't be isomorphic to a P1. So that's a way to quickly distinguish a P1 from another curve by computing this kind of degree.